the second office hours video for section 3 of the quadratic formula. And there's a pretty typical sort of situation in physics where you launch an object and it moves through the air. This is a side view on flat level ground, and it lands some distance away. So you can imagine hitting a baseball or kicking a football or shooting an arrow or something like that. This is called projectile motion. And projectile motion is a good example of a place where we can use the quadratic formula. As you're going to see later on, there is the general equation of motion in the vertical direction, which looks something like this. Y stands for the final vertical position. Y sub 0 stands for the initial vertical position. V sub 0 y stands for the y component of the velocity, the initial value of that y component, times time, the time coordinate, and then 1/2 times the acceleration in the y direction, so the y component of the acceleration, times the time squared. So you can see that since time is squared, you might end up using the quadratic formula in this. And that is in fact true. You can use the zero product rule to factor, or you can also use the quadratic formula. What I'm going to do is put in the values for these physical variables, and these values are not going to be numbers, they're going to be symbols. So, well, some of them are going to be numbers, but you can see that the object starts out on the ground. So I'm going to say that the ground is at an elevation of 0. So the initial position in the vertical direction is 0, but it also ends up on the ground. And so the final vertical position is also 0. Now what about the initial velocity in the y direction? You're going to see later that finding the y component of a vector, if we express the angle in the standard way, would be to take the magnitude of that vector and multiply by the sine of the angle. So in the diagram, if I draw the initial velocity vector, that angle is right here. It goes in between the vector and the positive x-axis. Now for projectile motion problems, the acceleration in the y direction is caused by gravity. So gravity pulls things down, causes them to change their velocity, and the downward direction is negative. And so if I were to write this in terms of a symbol, the y component of the acceleration is negative g, g for gravity. And g has a variety of numbers depending on where the projectile is being launched. On the surface of the Earth, it has a particular value which we've measured. This could also happen on the Moon. So I've been told that Neil Armstrong played golf on the Moon. In that case, the value of g would be smaller because the gravitational field on the Moon is smaller than it is on the Earth, and so on. You could be really anywhere. You could put in any value for the acceleration due to gravity g, and this analysis will work. So right now I'm just leaving it as a symbol. So if I put those numbers and symbols in, we get this. So 0 equals 0 plus v sub 0 sine of theta times time minus 1/2 g times time squared. So we've got a quadratic. You can also use the zero, you can factor it and use the zero product rule. But I will use the quadratic formula on this, just to show you that you can also do it even if the equation that you have, the constants aren't numbers but symbols. So let me just multiply everything by -1 and rearrange it just to make it a little easier. So -1 times the squared term, it becomes positive. The linear term, when where t is raised to the first power, becomes negative. And then plus 0 equals 0. So you can see, if you look at this, that a, the coefficient of the squaring term, is 1/2 g. We do this a lot in physics. Use a symbol for something without explicitly putting in the number, so we can use it in a variety of situations. B is equal to minus v sub 0 sine of theta, and c is equal to 0. The constant term is 0. So if we put that into the quadratic formula, minus b plus or minus the square root of b squared minus 4 times a times c. Well, you can see c is 0. So that's just going to be minus 0. And all of that is divided by 2 times a. So a is 1/2 g. And so if you simplify this, you get v sub 0 sine theta plus or minus. And the next term is you square that, and you take the square root, and those two operations cancel. So you get plus or minus v naught sine theta. And then the 2 and the 1/2 cancel in the denominator, so you get all that divided by g. So if you put in the plus sign, you get 2 v naught sine theta over g. I'll write that up here. 2 v naught sine theta over g. And if you put in the minus sign, the numerator cancels and you get 0. So you could also have t equals 0. So what do these two times correspond to physically? T equals 0 is the time when the object was on the ground, over on the left side, right before it was launched. And the other time, 2 v sub 0 sine theta over g, that's the time when it's on the ground after it's flown through the air, when it hits the ground on the right side. So these two times are physically real. And notice that one of them is a number, 0. The other value for time involves a bunch of symbols, but that's okay, because now we can use that result in a variety of circumstances. When the projectile is launched at different speeds, at different angles, and the amount of gravity that's present, if that changes, we can account for that also. You'll see this is basically the way physics is done, is to try to keep things as general as possible, as long as possible. So a lot of times you'll be working with symbols that are constants, along with numbers. Sometimes they'll all be symbols, sometimes some of them are symbols and some are numbers, and in rare cases they'll all be numbers. So I just wanted to show that to you, so you might start getting used to seeing things like that. But everything still works the same. Whether you're working with numbers or symbols, the rules of algebra and using the quadratic formula, everything still works the same. It just, for some of you, might take a little bit of getting used to. So I hope that helps out. Good luck.